Hi guys, it's a guy Olumide, and today we'll be solving another one of the most commonly asked tech interview question. Um, it is the Count Highland DSA problem. So it's a DSA problem that is commonly asked by top tech companies including Google, Amazon, Netflix, Meta, Apple, Microsoft, and other top tech companies. The problem statement states that given a binary matrix representing ones and zeros as land and water respectively, that is ones as land, so each ones in this matrix represents 1, is a binary matrix because it consists of 1 and 0, right? And then ones represents land while zeros represents waters. We are asked to return the number of island, whereby an island is formed by connecting adjacent lands 4 directionally, up, down, left, and right. So we are giving this example input here that actually consists of 2 islands. And why? Because this is one island here, whereby it contains lands, a number of lands that are connected 4 directionally. This set of lands here forms an island, and this is another set of lands that form an island. So this is the input matrix that is given in this visual here, and this is the corresponding output, which actually corresponds to 2 island form. This is the first one form right here. Write this 4 lands now, and this is another island right here. So how do we solve this problem? Fine, this problem is asking us to return the number of islands that are formed by connecting adjacent lands 4 directionally, and but let's consider a situation whereby our input have just 1 island, right? In this same example input that was given to us, there are 2 island, but let's simplify the problem to consider a situation whereby we just want to find and want to navigate through a single island in the input. So just like in this case whereby we have just 1 island now. So we can see that when we iterate through each cell in this matrix, when we get to the cell corresponding to the first row and the second column, we encounter the very first land in the matrix. So let me say the very first one, which represents a land, right? So one key observation is that we can, by actually moving horizontally or vertically through the board, we can actually get in touch with every land cells in a island, or every land cells that forms a island, by moving horizontally and vertically, and therefore we can actually compare this board or the island in this board as a graph, as a graph structure, whereby the nodes represent, or the cells here represent the node, and then the edges is representing their horizontal and vertical connection, just like how this particular one is connected vertically to this other one, and this other one is connected horizontally to this other one. So it represents the edges, their connection between each other. So we see that by effectively navigating horizontally and vertically, we can get in touch to each and every land cell that forms this particular island. And what I'm trying to say is that, look at this one here. Let's say fine, we get our first island, our first land cell from this particular cell here. So navigating horizontally, we can get in touch with this one here, and then further navigating that's navigating vertically, we can get in touch with this one here, and then further navigating horizontally, you can get in touch with this, and horizontally you can get in touch with this, and vertically from here we can also get in touch with this one here, and thereby we can actually traverse through the graph. So this actually simplify, and we can traverse through the matrix, right? This actually signifies and illustrate that we can actually use a graph traversal algorithm in order to reach each and every land in this particular island, right? So, and we'll be using the DFS graph traversal algorithm, so as to recursively call it on the O component on each of its child and children. So but now I'm just trying to give this this particular cell. I'm just trying to give this particular matrix here and a graphical illustration to signify that we can actually use recursion to traverse through each land cell until we get to the very last land cell in the island. So that's for a matrix with just one island. So considering the depth first search method now as we traverse the matrix, we need to keep track of visited cell, and we can do that in two ways. So first of all, we can use the arch set to keep track of the coordinate of the visited cells. Like now, look at this particular, as we traverse through the board, we get to a 1, so we have to keep track that, okay, this particular island or this particular land cell have been visited. So and then we can either store the coordinates, which means 0, 2, which represent the coordinate of the cell, the row and column. We can store it in the arch set now, so whereby we'll be looking up into the arch set to try to check if that particular coordinate is in the arch set, that is, if it has been visited before. But we can also do another way of setting it in place to -1. I mean, setting the value at that cell to -1. So in such a way that whenever we encounter a land cell, so and then because we have visited that land cell, we are just gonna change it in place to -1. So the next time we come across it now, we will know that it is not a land cell, because land cells are actually 1 and not -1 or 0. They are just 1, right? So that's another way, and we are gonna go for that way because it doesn't require an extra space, right? It doesn't require a arch set or any data structure. We're just gonna change it in place. So now having visited this particular land cell and recorded it as -1, they want to visit its neighboring cell. So we by performing a DFS on its neighboring cell, what I'm trying to say is that by just trying to go into its neighboring cells to look for subsequent ones, we are gonna see that we just have just a single neighboring cell with a 1, right? So this is it here. So this is a neighboring cell, the rest are actually 0, 0, right? So this is just one neighboring cell that have a 1, and then we're gonna record this particular neighboring cell as visited as well. So this is it here, the graphical illustration. So we are gonna record it as -1 now, and after recording it as -1, we're also gonna traverse to the neighboring cell of this by trying to do a DFS on the horizontal and vertical on its horizontal and vertical cells, right? So because these cells actually just behave like nodes, you understand, in a graph, and then their vertical and horizontal friends or neighbors or neighboring cells actually act as connection. So now similarly, this particular cell just have one neighboring cell with a 1, that is, it has only one neighboring land cell, right? So I'm gonna navigate into that cell now and visit and mark it as visited also. And how we do it is by setting it to -1. So we have it right here, and now we can see that this has 2 neighboring cells. So I'm gonna visit the first one, the horizontal one, and visiting, we're gonna set it to -1, right? Then we're gonna go back and visit the next neighboring cell or neighboring land cell, which is this one here, and we're gonna set it to -1 or as well. So this way now we can see that we have actually navigated through all the lands in this particular island. So this is what we call an island, a group of land that are surrounded by ocean or sea or zeros, right? So okay, so now that we have effectively navigated through the lands and we have marked them as visited, so we don't go about visiting the same island again, we are going to increment the island, our property, our count property that counts the highland. So we're going to increment it by 1 because we found and we've traversed in an island, right? So we're going to increment it by 1. So but now let's talk about matrix with multiple islands. Don't forget that this illustration only contains a single island, right? So now let's consider a matrix that now contains multiple islands. So we're going to be doing similar things now, just like the one we did previously for a single island. So and what we want to do is that first of all we search through the matrix starting from cell 00 until we find a land cell, right? We're going to navigate through the matrix until we find a land cell. So upon encountering a land cell, we are gonna explore its island using DFS, marking each land cell we encounter as visited to avoid visiting them again, just like we did repeatedly here, right? So visiting the marking it as visited and try to explore any other neighboring land cell. So, and the third step is to increment the count by 1. So island count should be incremented by 1, indicating that we've discovered an island. So that is after we have visited every neighboring land cell to that particular land cell, right? So we mark the land cell as visited, try to visit its neighboring land cell, mark them as visited, and after we have navigated through all the neighboring land cells at that point, and there's no more neighboring land cells anymore, just like in this case, whereby there's no more neighboring land cell, we are just gonna increment our count by 1. And then for multiple, the only difference or the only addition for multiple islands is that we keep searching the matrix for any unvisited land cell until we find one. Then we repeat the step again. So imagine this this step now. We found an highland here and want to explore the highland. So after exploring the highland now, so after this place is an highland too, so we're gonna explore it just like we discussed the other time. Then after that, now we're just gonna keep navigating through the board again. Don't forget that it is at this point 0 that we find the first land cell in the highland, right? And then after finding it, we try to navigate the other land cell in the highland. So now that way we have found the first island, so we just try to continue navigating through the board, starting from the second cell, right? Because we are currently at the first cell where we found the first island, or let me say the first land cell in the first island, and when we navigate through, we have everything recorded as -1 -1 -1 right here. So we just have to continue from the very second cell, right? But luckily, because we have marked it as visited, so it's no longer a 1 because it has been explored. So this is a -1. So we just continue navigating through until we find another valid one now. So which we're gonna find here, and then we're gonna explore this one again to give us this, and all islands have been explored that way. So, and then don't forget now to traverse the matrix. An addition now is that to traverse the matrix 4 directionally, we are going to be using an array, DIRS. So what I'm trying to say in essence is that imagine we found a land cell now and we mark it as visited, right? So but we have to explore the neighboring land cell to that particular land cell. So we can use this array, we call it direction array, whereby it represents it's actually an array of tuple where each element in the tuple corresponds to the row and column. So this is row, this is column, this is row, this is column, this is row, this is column, right? That's how it goes. So, and what this means is that a direction array, so it actually points to the top of the, imagine this particular one now, it's or let me say imagine this particular one here, right? It actually points to the top. I mean its neighbor, its 4 neighbor, it points up, left, bottom and right. So when I say that -1, 0 right here, it actually points to a row of -1 and a column of 0. Now let's figure that out. A row of -1, consider that this is the cell now. A row of -1 will be a row before this particular row. Don't forget that this is a row here, right? This is one row here. So a row of -1 actually signify here, while a column of 0 signify the same column, right? So this is pointing right here. So right is pointing right at this 0. So similarly, 1, 0, this top 1, 0 means what? 1, 0. So it's pointing to the next row, which happens to be the last row, and the same column. So similarly, 0, -1 also work, but in the column base now. So and what it means is that 0, -1, so the previous column, and then 0, 1 means the next column. So it's just there to represent the direction, so that we can be able to navigate through the array through the board 4 directionally. So we'll be going to the code implementation now to put every one of the logic that we explained now to action, to put it into code, and you're gonna really enjoy this part. Alright, let's go into the code implementation for the count island DSA problem. So we're gonna be defining the function count islands, right? And it's gonna be taking in a matrix, which is the matrix of islands. so which is actually list of integer. So right, and then we are gonna be returning an integer which actually represent the number of island, right? So let's drop the matrix now that will be passing in, right? So this is the matrix that is given to us in the problem statement, and let me just call the function count islands of matrix, right? So now in the function, what we're gonna do is that let's first collect the length of the row and the column. So length of matrix, and why? Because we need to iterate through each cells in the matrix, right? So we want to get the length now. So similarly, let's define a variable islands that will help us to keep track of the number of islands so far, right? And let's define our DIRS, which is the direction of vector array, so that is gonna point to the adjacent neighboring cells, right? So minus 1 comma 0, so minus 1 comma, let's call it 0 comma minus 1, right? And then 0 comma 1 and 1 comma 0. So these are the adjacent cells. Now these are pointers to the adjacent cells at any given cell, right? Fine. Now let's iterate through the cell for R in range of M, so iterating through each row, and then for C in range of M, iterating through N. Now iterating through each column, and then we want to check if matrix of R of C is equals to 1, that is if this is particularly a land, I mean a land cell, right? Then we want to call our DFS function, passing in the row, passing the column, the matrix, and then direction. So right, so and at the same time, because we have encountered we eventually encountered a land cell which actually will link us to the corresponding land cells, neighboring land cells in that island. So we want to increase our islands by 1, right? Why? Because we come across a land cell, so we increase our island by 1, and after that's after we navigate through we visited through each neighboring land cell for that island. So now let's define our function DFS, right? So it's gonna be taking in a row, it's an integer row, an integer column, a matrix which is actually list of integer, right? So, and also it's gonna take in the DIRS, similarly a list of integer, right? Okay, so now what we want to do in our DFS first of all is that we want to mark the particular cell as visited. So matrix of R of C is equals to -1, so it has been visited that way, right? Okay, after that, now what we want to do is that we want to navigate through adjacent neighboring cells for DIR in DIRS, right? So if okay, now let's create the row for this adjacent cell. Don't forget that the adjacent cell will be horizontally, probably left, right, or up or down, right? So now let's create the row and column now, because it won't be the exact row and column for this particular cell. Is either to the left or right, or so we're gonna be adding R plus DIR of 0. So because we know that DIR of 0 always represent the row and DIR of R will represent the 1, so DIR of 1. So and then now we want to check if it's within bound. So we want to check if this row and column won't give us an index error if it is within the, if it's between 0 and the, if the row is between 0 and the length of the row, I mean the row of the, or total row of the matrix, right? For this particular matrix now, the row is 1 2, this is the row 1 2 3 4, right? The row is 4. So if the row that we calculated right here, if it's between 0 and 4, so that's what we want to check, so that it won't give us an index error. So if it's within bound of row column, and we're passing in the matrix because we want to check it out if the row and column is within bound in the matrix. So, and if it is, fine. We also want to now check if matrix of row of column is a 1, that is, if it is actually an island, then we want to visit it, we want to also navigate through its neighboring lands. And because of that, so if it is a 1, we just want to call DFS on it again, so we can visit it and we can mark it as visited and navigate through its neighbors. So row column matrix and DIRS, right? So but this time we're not going to set it to 1. Why? Because DFS is called whenever we are navigating through to find the rest of the land cells in a island. So each time we encounter a new one, we are going to be increasing the island there, right? So now let's create the is within bound function. Is within bound function, right? Okay, we are going to be passing in the row into it, which is an integer. We're going to be passing the column as well, which is an integer, and the matrix, which is a list of integer, just like we can see here. So it's a list of lists, whereby the list inner list or nested list contains integer. So now we just want to simply return whether 0 is less than equals to r, that is, if the row is either is between 0 and len of matrix, because len of matrix actually represent the row. So the length of this matrix is gonna give us 4, because we have 4 rows, 4 lists inside the list, right? So, and 0 is less than equals to c. Why we are putting it less than equals to? Because c can be 0, right? It's fine. So, but it must not be greater than or equal to the length of matrix of 0. Why? Because it is 0 index. So this is index 0, this is index 1, this is index 2, this is index 3. So whereas the length of matrix of 0 is 4, so but the index is between 0 and